Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover vector-valued functions, more specifically the derivatives and then eventually the tangent lines. So really, what is a vector-valued function? Well, we'll do it in 3 dimensions. It can be in 2 dimensions as well. But what we say is r of t is going to be equal to, some f of t I plus some g of t j plus some h of t k. Now, we can also write this in component form if you'd prefer these triangular brackets, but, the x coordinates defined by the f function, the y coordinate by the g function, and the z component is by the h function. So we'd say, f, g, and h are functions of t. Parameter t. Where t is going to live in some interval. So if I want to find their derivatives, well, r of t, and a lot of times we put like a little vector on here. It's hard to do bold in on a whiteboard or on this glass board, but this is a vector valued function because this is a vector. And the way we think about this, let's just talk about it graphically for a hot minute. So what we have is this is going to define, multiple points in this 3 space. So this is going to be the point, f of t, comma, g of t, comma, h of t. And now this vector r, is going to be the vector that goes from the origin to that particular point. And when I move, or when I, use the functions f, g, and h, this point's not going to be stationary. It's going to move depending on the values or the outputs of f, g, and h. So what you'll eventually get is, actually, let's do r like in a blue curve so you can get an idea really what this is this is going to be equal to, say, maybe some curve in 3 space where these points are solution points of this r of t. So what I want to do is I want to find its derivative and then eventually its tangent line. So what we're going to know is in order to find, say, this thing's tangent line, what I'm going to need is I'm going to need basically a solution point, and we have a ton of them. We need a specific solution point, so for some value of t, and let's say this is our solution point right here. And that means its tangent line is going to be, tangent to this curve through that particular solution point. So it just so happens to, this is also a vector valued function. It just happens to be, a line. And let's call this L of t for lack of a better letter. So L of t, or our tangent line, is going to actually be equal to the initial solution point at t equals 0. So this is going to be equal to some r of t naught plus, and we're going to say v of t naught times our parameter t. Now, r and v are going to be vectors. Unfortunately, I haven't defined what v is. Well, just like I said, this is a lecture on derivatives as well. So the derivative of r of t, which is also v of t, so we can say dr dt vector, which we also say is v of t, and v of t for velocity, is nothing more than the derivatives of each one of the components. So this is going to be equal to f prime of t I plus g prime of t j plus h prime of t. Okay. So in order to find this tangent line, I need a solution point. I need to know, what it crosses. Remember, this function defines all those blue dots. And at that particular t value that I might want, so let's call this at this particular t value. Different t values are going to give you different points on this blue curve. And then at that exact same t value, I'm going to need its velocity vector, which really goes in the direction I want to use direction, the word loosely. A lot of times when we say direction, we mean unit vector, but it doesn't have to be a unit vector. So if I say v of t is this v of t naught, this yellow thing, what I'm saying is it's going to have this kind of direction. So it's going to go through this red dot and be in the direction of v of t. All right, so let's find a couple derivatives, and then we'll find a tangent line or two. So here's our first example. I'm giving you a function f of t, which is 2t plus 1i, 5t minus 4j, and then negative 5tk. And I want to find its first and second derivative, really the velocity and the acceleration of this function at this given t naught. So this t naught of 2. So let's do that again. So here's our example. Given a vector valued function, find their derivatives. Its first and second derivative. Find the velocity and the acceleration. Try that again. Okay. Here's our first example. Given vector valued functions, find their derivative and second derivative. But basically what I'm asking you to do is find the derivative, which is the velocity, the second derivative, which is the acceleration, at this given t naught. So here's our function, 2t plus 1i, 5t minus 4j, minus 5tk, and I want to find it at t naught, which is equal to 2. So in order to find the first derivative, it's going to be, well, dr dt, and another way of writing dr dt is going to be v of t, which is its velocity vector, and it's just going to be the component-wise derivative. It's kind of exactly what we expect. Derivative of, the ith component, derivative of the jth component, derivative of the kth component. So the derivative of the ith component is 2i plus the derivative of the jth component is just going to be 5. So then that's going to be our j. The derivative of the last component, which is going to be equal to negative 5t, which is going to be minus 5k. Now, what you'll notice is this velocity vector is a constant vector, and the reason why it's a constant vector is because the original vector valued functions align. You can see that these coefficient functions are linear functions, so this draws a line that goes to the point 1, negative 4, 0, because there's no constant over here, and it's got a parallel vector that goes 2, 5, negative 5. So again, I can say that this goes to the points, 1, negative 4, and then 0. And then it's got some directional vector, and just disregard, this is not it's drawn to in the correct directions because it's hard to do 3D. But this vector right here is going to be the vector, say, 2, 5, negative 5. Having to do the coefficients for the t. So what that's going to do is this vector value function r is going to be, this line right here. And what we know is if it's linear, just like in calculus 1, the derivative of lines are constant. So this is a constant vector because this is the derivative of a line. Now, if I want to find its acceleration vector, which is going to be the second derivative of r with respect to t, and or I can say, dv dt, or we say a of t is just going to be the derivative of the velocity vector. So since this is a constant vector, the derivative of 2 is 0i, derivative of 5 is going to be 0j, and the derivative of negative 5 is going to be 0k. So it's got no acceleration. Actually, what's kind of interesting is it has a constant velocity and it's got 0 acceleration. So if you're going to draw this line, say starting at this, at this point here, which is 1, negative 4, 0, what it's going to do is it's going to draw very linearly. It's actually going to draw at a consistent speed, essentially, or consistent velocity, as opposed to something that might, when you draw it, might speed up as you go. But this one doesn't. It has a constant velocity, so that's why it looks like this. Now, since it has a constant velocity, that means the acceleration is going to be equal to 0. So just like when you're driving in your car, if you're driving at a consistent 55 miles per hour, it doesn't really feel like you're moving because you're driving at a constant velocity. So that means your acceleration is 0. So you don't feel anything. Now I wanted to do this at this value t naught, which is equal to 2. Now, what we'll notice is since these things are constants, evaluating this at t equals 2 is really no different because there's no inputs left over here. So if I wanted to find, at 2, evaluate this at t not is equal to 2, evaluate this at t not is equal to 2, it doesn't matter. There's no inputs here, so you're going to get the same values or the same vectors. So here's our second example for finding the velocity of the derivative. So r of t is going to be the cosine of ti plus the sine of tj plus e to the tk, and I want to do this for t naught, which is equal to pi. Now, before we do this, let's just kind of draw like the picture of this thing. It's something that should be somewhat familiar. So this piece of it specifically, when I have cosine of ti plus sine of tj, remember that the x coordinate is going to be equal to your cosine of t, and then your y coordinate is going to be equal to the sine of t. So if I put this in parametric form, that's the x and y, and then finally your z is going to be equal to e to the t. But if I'm only looking at like straight down on this thing, what you're actually going to look at is this is nothing more than a unit circle, where x is the cosine and y is the sine. So if I was going to graph, just this part without the e, you're going to see that you're going to have that unit circle there. Now, what does e to the t do? Well, e to the t is going to make z, rise exponentially. So what's actually going to happen, instead of this thing being a flat, if this was 0, this would be the curve. If this e to the t was 0, but it's not. So what it's going to do is it's going to grow exponentially. So it's going to look like this. So it's going to grow exponentially. Now I'm trying to make it look, the Z's kind of grow fast enough. I don't think I did a fantastic job of that, but it's really going to grow very, very, very quickly. Okay. So now that we have an idea of what the thing looks like, let's go ahead and find, the velocity acceleration vectors at this t naught. Okay, so v of t, which is going to be the derivative of this thing. The derivative of the cosine is negative sine of t, I. Derivative of sine is going to be cosine of t, j. Derivative of e to the t is going to be equal to e to the t, k. Now, that means our velocity at pi is going to be equal to minus the sine of pi plus the cosine of pi. Oh, I need to have an I here, a j here to say what component I'm in. And then plus e to the pi k. Now, remember, unit circle, we're talking right here. So this is the point -1 comma 0 because that's angle pi. So, the sine being the y coordinate, and so this is going to be equal to 0. The cosine will be equal to -1. So this is going to be equal to 0i minus 1j plus, well, e to the pi k. Okay, so now a of t. A of t is going to be the derivative of, remember that we have to go off we have to go off this velocity vector. So if I'm going to if I'm going to find a of t, I have to go back to the original velocity vector because if I take the derivative of a constant, we know we're going to get 0. So first, we're going to take the derivative of negative sine, which is going to be minus cosine of t I, the derivative of cosine, which is going to be minus sine of t j, and the derivative of e to the t is going to be equal to e to the t k. Now, the acceleration at pi is going to be minus the cosine of pi I minus the sine of pi j plus e to the pi k. And again, over here at pi, cosine is going to be equal to -1, so negative -1 or 1i. Sine is going to be equal to 0. And then plus e to the pi times k. So last thing I want to do is I want to find a tangent line to a couple curves, and then we'll finish this. All right. So given the vector valued function, find its tangent line at the given t naught value. So I'm getting this r of t is going to be equal to this line, and I'm going to find its tangent line, and It's going to be kind of what you expect. So without giving it away, let's just kind of do the work and then see if it makes sense to us when we are done. So, uh, in order to find a tangent line, what we know is that our line, let's call it L of t for a tangent line, is going to be equal to it's r of t naught plus v of t naught times that parameter t. Now, where t naught is going to be equal to this 1. So, again, when we're looking at a line, what I know is that our curve, let's call this curve r of t, is going to look, say, something like this. And if I want to find its tangent line, I don't know, let's say about here. Let's say that's our t naught value. That tangent line is going to look like this. So in order to find the equation of the tangent line, I'm going to need a solution point. And, well, there's one right there. That blue solution point, this thing right here, is going to be equal to, um, you know, r of, in this case, 1. Now, I'm also going to need to know a parallel vector that goes with this. So the parallel vector that goes with this is going to be equal to this thing right here, and that is going to be equal to v of 1. So just like in algebra, in order to find the equation of a line, we needed a point and a slope. But now, since we're working in 3 dimensions, the slope isn't good enough because you can't just do rise over run. I have 3 dimensions. Changing y over changing x isn't going to work for this. So what I'm going to need is I'm going to need a parallel vector that goes in that particular direction. So it's still a line and a direction essentially, and that's what the slope used to give us, was that direction. Okay, so let's go ahead and find. I need to find r of 1. I'm going to have to find v of 1, and I can plug it into this formula. Okay, so r of 1. Sorry. R of 1 is going to be equal to, remember, this is the solution point right here, so I just have to plug 1 into this thing. So this is going to be 3 times 1i plus 2 times 1 minus 1 j, and then finally plus 5 times 1 minus 2, and this is going to be our k. So we're going to get the point 3i. 2 minus 1 is going to be plus 1j, and then plus 3k. So, this point right here is going to be the point 313. So 3, comma 1, comma 3. I know it's a vector, but it's the vector that goes from the origin to that point. It's how we define vector value functions. Now, I'm also going to have to find its velocity at 1. So before I do that, I'm going to have to find the velocity vector. Well, v of t is going to be the derivative of this thing. And since they're all lines, they're just going to be the coefficients. So this is going to be 3i plus 2j plus 5k. So this vector right here is going to be the vector, 3, 2, 5. So finally, plugging this into, this is going to go right here. And then similarly, this is going to go right here. So finally, with L of t, let's do it pink. L of t is going to be this first vector. We can say 3i plus 1j plus 3k. And then we're going to have to add it to this velocity vector, which is going to be, 3i plus 2j. Some room here. Plus 5k. And this is all times our parameter t. Now we can add the i's together, and we're going to get 3 plus 3t, so 3 plus 3t I plus 1 plus 2t j, and then finally 3 plus 5t. Okay. So it's what's interesting is this original function was actually a line. It doesn't look like the blue curve. The original function was actually a line. So the tangent line to the line is going to be itself. Now, even though these things don't look like the same curve, they actually share the same values for certain t's. So, say when t is equal to 0 here, we're going to get 0, -1, and then -2. And I can say there's another t over here where I get exactly the same thing. And it looks like it's t is equal to -1 is going to give me those same 3 points. And then so on. So, this will still plot the exact same line as this one, because a tangent line to a line is going to be itself. All right, let's do another equation where I'm not talking about a linear equation. Let's do something that's not. So the second example, we're going to do the same. Looking straight down on it, you're going to see a unit circle, but the z is going to move, cubically up. So again, in order to find our L of t, our tangent line, it's still going to be equal to r of t naught plus v of t naught times t. So I'm going to need the initial point, which is going to be our vector value function defined at pi over 2, or evaluated at pi over 2. And then I'm also going to need to know the velocity at that pi over 2. And then I can find these, these coefficients. So r of pi over 2 is going to be equal to the cosine of pi over 2i plus the sine of pi over 2j plus pi over 2 cubed k. And this is going to be, well, the cosine of pi over 2 is going to be equal to 0i plus 1j plus pi cubed over 8. Okay. This is still just a constant. Now, our velocity vector, we're going to have to take the derivative of the original function. So the derivative of the cosine is going to be minus sine of ti plus cosine of tj plus 3t squared k. Now, the velocity at that particular pi over 2 is going to be minus the sine of pi over 2i plus the cosine of pi over 2j plus 3 times pi over 2 squared k. And the sine of pi over 2 is going to be equal to 1, so this is going to be minus 1i. Cosine of pi over 2 is still 0, so plus 0j. And pi squared over 4 times 3, so plus 3 pi squared over 4, and that's going to be k. Now, again, what's going to happen is, this velocity vector is going right here. And then similarly, an initial point is going to go right there. And we still have to multiply by that parameter t. So L of t is going to be equal to 0i plus 1j plus pi cubed over 8k. And then finally plus our velocity vector, so minus 1i plus 0j plus 3 pi squared over 4k times t. And we can combine these things as far as the x-coordinate, y-coordinate, and so on. So 0 minus 1ti, that's just the coefficients in front of I with that t, plus 1 plus 0tj. I know the zeros are redundant, but I just want to show where they're coming from. And then finally plus our pi cubed over 8 plus 3 pi squared over 4 times tk. And again, you can tell this is a line, these linear coefficients. So that is our tangent line. So if you enjoyed the video, please like and subscribe. Thank you.